Okay, so we're going to do arrays. And let's look in here. Single dimensional arrays. Well, first of all, an array is a very simple idea. It's just a sequence of values. That's it. Things put in a row. So here's a sequence of values: 3, 22, 5, 14, and 6. And when we list them here, we're separating them by commas. And this statement right here, this is the declaration of an array A. Is the name of the array is A. And these symbols right here, this open and close brackets, are part of that declaration. So that means A is an array. If we took those out, it would say well, A would just be an int. So here's the data type. So A is an array of integers. We could have a double A, right? Then it would be an array of doubles, double precision floating point values. Or it could be an array of string, or an array of char, an array of float, an array of vector, an array of arrays. So any data type is acceptable to construct an array. But once you declare the data type for an array, every item that you put in the sequence, every item that you put inside this array container is of that type. So we can't put a double into A. I mean, we could probably, but it would chop off the fractional component. We would just get the integer component. So an array is, a sequence of values of some specified type. In this example, they're of type int. And they're stored sequentially in memory. So you know that if you look at memory, the 3 is stored first, and then after that, in the very next storage location, or group of storage locations, because these ints are stored across 4 bytes. So 3 occupies 4 bytes. Then the next 4 bytes has got a 22 in it. The next 4 bytes has got a 5 in it, and so on. So they're contiguous. That's the word we use, contiguous. And array indexing starts with 0, just like counting. So we've been talking about counting already. We talked about arrays a little bit with strings. A string is a type of array. It has an array-like functionality to it. And you use the brackets to index into the string to pull out individual characters. We looked at that. Now we don't have characters, we have something else. We have integers in this example, although we could have characters. And we use index values starting at 0 to identify the items in the array. So this 3 is in position 0. This 22 is in position 1, and so on. So we start counting the positions from 0. 0, 1, 2, 3, 4. So the last position is position 4. That means it has 5 items. So the array size and its last valid index are off by 1. They differ by 1. So we can access values in the array using this notation. So it'd be like A bracket 0. And that's the first item in A, the item in position 0. That's the first item. Maybe we should say the 0th item. No, we don't have that. We don't use 0th item. So we start counting at 1 as humans, but in hardware starts counting at 0. This is the item that's in position 1, so this prints a 22, and so on. Normally, we use a loop to access the values in an array. So we can print each element in A by embedding this statement inside of a loop. See, we're just printing the value at position I. What's the value in A at position I? That's this expression. This is the value in A at position I. Practice that, on your own, that language and the concept. Because the main point of confusion with arrays that students have is they don't differentiate between the value at a position and the position number, or the index. The index of that number in the array and that number itself that's in the array. The distinguishing between those two things is the main confusion with arrays that students face when they first get exposed to this. So you have to practice distinguishing between those things. So look at the loop here. The loop I starts at 0. That's the first position in the array. That would be the 3 in our example. And then, so we created a variable I, set it to 0, and then we test the loop condition. And when the loop condition is true, we're going to do the substatements. And after we do the substatements, we're going to do this end of loop operation. We'll increment I. We could do something else. We can have any expression there that we like. But typically, you'll see an index being incremented, typically, but not always, but most of the time. So this way, this output operation is embedded inside this loop as a substatement. So I runs from 0 to 4. So we print A of 0, A of 1, A of 2, A of 3. We print A of 4. And then when I is 4, we do the end of loop operation so that I becomes 5. And then we execute, or evaluate the loop condition, and that evaluates to false, and then the loop is done. Here's an example where we create an array of 40 elements, and each element is of type double. The name of the array is B. We could have called it A again, or called it anything. Well, it has to be a valid identifier, but other than that, we can give it the name we like. So here is different. In this example, we have empty brackets because we're telling the compiler what to put in the array. So the compiler says, well, you don't have to tell me how big the array is because you're giving me all the numbers. So I know that the array is of size 5 because you're giving me 5 numbers. But in this expression down here, we don't tell the compiler what to initialize the array to. We're not saying, here's a list of values, put them in there. So now the compiler says, well, you didn't tell me what to set the array to, so at least you can tell me how many slots you want in the array. So we want 40 slots. We want 40 positions. So that number is put in here between the brackets. Now, this array is not initialized. It's uninitialized, so we don't know what's in B. In other languages, every other language I've worked in, B would be initialized to all zeros in this case. But in C++, that doesn't happen. I think unless B is declared as what's called a static variable, something like that, can't remember. There may be a case where B is actually initialized to all zeros, but in general, this no initialization happens here. And here's a special form. If we want B to be initialized to all zeros, we can give the size of B and then use an assignment operation like this with a single 0 in it, and it'll assign zeros to the whole array. Or we could put a 7 in here, and then we'd have 47s in the array. And let's do a little bit more with that right there. Let's do this. I'll show you some maybe unexpected behaviors. So we create an A. Say A is of size 40, and we initialize it to all zeros. And so we can print. Well, let's use 5. Let's use 5. We don't need a big number. So let's print the contents of A. All zeros right there. And it's hard to read, so let's fix that. I'm going to print the blank here. And then after the loop, let's output a new line. So it's easier to look at as we do our experiments. There's the contents of A. Now if I put a 7 in there, oh, darn it, that happens once every couple of weeks. I'm hitting the wrong keys. All right, no sweat, we're going to go right back in there. All right, so 7. Now, what's it going to print? 5 7s? Or 1 7 and 4 zeros? What's it going to print? What would you do if it was your language and you were some human decided what the result should be? Some human said, oh, in this case, we're going to make the compiler do the following. What would you make the compiler do? This is how I do guessing. You know, when I say, oh, if I were to create this language, what would I do? And I would try that and do an experiment to see if I got it right. Okay. So what would you do? Would you put 5 7s in A? Or would you put 1 7 followed by 4 zeros? Because the array is of size 5. We already know that if we put a 0 here, we know that we get 5 zeros in A. We know we got that. But if we put a 7 there, what do we got? I was going to guess the other one. I was going to say 5 7s. I got it wrong. Look at that. I am totally surprised. I wonder if that's true for a different version of C++. Let's try that. C++ 11. Same thing. Okay. Wanted to change the version. So I just surprised myself. I should have said something. So it's a 7 followed by zeros. Look at that. So I did this. I get a 7, a 3, and then 3 zeros. Yeah. And I don't need to use the newer version. I'll use the old version. Okay. So I got that one wrong. Now this is, like a double here. What if we did this? We could say A of 0 is 7, and A of 1 is 3. So we can make A of 2 equal to 8. So that's another way, that's how to store an 8 into position 2. That's the syntax for that. Make this a 4?
No, change 5 on what it says right there.
This one here?
Yeah, when we change that one.
If I make that a 4?
Yeah.
Should I leave these out? What do you think it's going to print? What is this going to print? What do you think? You got to have a guess.
4 digits is the 5.
So it's going to print 7380.
Yeah.
It's only going to print 4 things. That's right. It doesn't mean that's the array has only got 4 items in it. It's just that those are the values we accessed. What happens if we did this? Now what is it going to print? By the way, most languages would not run this. They would say, oh, out of range, index out of range exception. We'd get a memory exception. It would just fail, it would stop, it would halt. But in C++, the range is not checked. I think you can turn it on. There's an option to turn it on. But by default, it's not on, at least in the old versions that I'm familiar with. So what happens if we try to go to position 5, when the max position is position 4, right? But now we're going to try to hit position 5. Remember, once we hit 6, we exit the loop, so we'll never use 6. We'll use 5. We'll use A of 5. But A of 5 doesn't exist. 5, A5 here, it gives us, these values. 1, 2, 3, 4. I'll just put them in there. So there's, no, that's not right. That is right, isn't it? I'm going to do it like this. I'll put in the numbers that equal their index. So here, A of I equals I. So, this is position 4. There's a 4 in position 4. And if we change this to a 6, it's undetermined what happens. Because we're going to access memory beyond the array. And look, there's a 32767 in there. That might be the largest integer, actually. That could be the maximum integer. Is it? No, 32,000? No. It's not that small. No. Just there's some number in there because we didn't initialize. It didn't do what's called range checking. It didn't say, because when we got to A6 here, watch. We're getting to A6. Basically, it's doing this. A6, but A6 doesn't exist. And it's not even guaranteed that we're going to get the same result when we run it a second time. But we did. Oh, but look, then we get a 0. Oh, that's not A6, oh, that's A5. A5, sorry. It's A5. Because I hits 5 and we output A5 in the loop. And then just to show you that that's what was happening, there it is. So A5 doesn't exist, but it does exist. There is memory. There is, the compiler generates machine instructions that access memory that's past what we declared the array to be. And the language lets us do that. Other languages don't let you do this. What happens if we do this? 6,000. Now what's going to happen? What do you think? I think we're going to get like a memory exception because we're going to go past, when we execute the program, the operating system sort of grants a certain block of RAM to the process, and it's not allocating. So we're going to try to access memory beyond that that allocated block of memory. So the operating system will intervene. See, segmentation fault. We can't access that. Or maybe it's the hardware that causes a problem because of the way we have virtual memory or something like that. Yeah.
For int A5, since there's only up to position 4, it would still work with int A4, right? Since it's just the block is larger.
Say one more time.
Since when we take the array size to be is 5, which is technically 6 positions, it would still work the same way before, right?
You said A5, right?
Yeah.
There's 5 positions.
Yeah, so it's 6, isn't it?
Huh?
Is it
No. 5. There's 5 positions.
So
This array has 5 positions.
that's including.
That's the size of A.
Yeah.
Starting at position 0 and ending at position 4. You got to get used to that, right? Off by 1 problem. It's going to haunt you now.
Yeah, I figured it out.
You got
just
it?
says how many positions starting at 0.
Yeah, that's right. How many positions starting at 0? Exactly. So the last position is 1 less than the size. The position is 1 less than the size of the array. Let's see what else we're doing here. Multi-dimensional arrays. So, we can have any number of dimensions. These are just 2-dimensional arrays. I don't show 3-dimensional arrays, but they exist. And we can take a look at this. I guess we'll just do this. Now the code is, I wrote that code, so naturally think it's okay. So let's see, this. So we'll use assert here. So we have a 2-dimensional array. You can think of it as like a table of values with rows and columns. So I'm using R to represent the row index and C to represent the column index. So what's the value in row R, column C? What's the value at row R, column C? And it should be 0 because we initialize this 30 by 40 dimensional array to all zeros. So we have an array that has 40 columns and 30 rows. It's like a spreadsheet with the rows and columns. And then you have cells where you put values in the cells. I'm using integers over and over. Once again, you can use doubles or strings or anything you like. So if we want to look at every single value in the array and check it, we want to check every single value in the array and check that it's 0, right? Then we use this expression here. A of RC, that accesses the value at row R, column C. And then we want to compare that to 0. So that value at RC should be 0. So we pass that into assert. So if that comparison is true, assert just quietly does nothing. And if the assertion is false, that will fail. So that means that R and C have to range from the minimum to the maximum number. So the rows start at 0. The first row is row 0, and the last row is row 29. We could have written the loop like this. For R equals 0 until R is less than or equal to 29, and so but execute the loop when R is less than or equal to 29. Maybe that's how people think. This works. This is the same. This is an equivalent way to write it. It's just that when you look in the textbooks or you look at people's code, they just don't tend to write it like this. You can write it like this, and it works correctly. But you tend to see this. It's just a tradition. And it springs from hardware, actually. Code was written first very close to the hardware, and then it evolved through, languages, assembly language, and then higher level languages on top of that. They stuck to this. So the row index starts at 0 and then goes up to 30, and then the loop is done when R hits 30. So we don't do anything when R is 30. But the last thing we did was when R was 29. The last time we did something was when R was 29. So for each R that we pick here, we're going to run C through all of its numbers. We're going to run C from 0 to 39 and use 39. But when we hit 40, then that inner loop is finished. So this is the inner loop. That's a substatement. So the statement that starts in line 9, that's the outer loop. That's one thing. That's one statement. 9 through 13 is a statement. It has one substatement. I have highlighted the one substatement. So in the outer loop, we set R to some number, like maybe it's at 5, then it goes to 6, and so on. So R is something. When R is set to something, then we execute the inner loop. And the inner loop repeats line 11 for C equals 0, C equals 1, C equals 2, and C equals 39. You're just going to have to think through that a bit, okay? It's a loop within a loop. And that's how we range across every value in A. And let me show you this. Let's make this fail. So we say A. Well, let's run this first of all. Let's watch this work. All tests passed. As I said, A of 29, 39, that's the very last position in A. 29, 39. Because, the rows start at 0, go to 29, columns start at 0, go to 39. So this is if you think of it as a spreadsheet, this is the bottom rightmost corner of the spreadsheet. We're going to put a 1 in there. So we should hit that in here, right? The loop. So this assertion will now fail on that last item. There it is. It doesn't tell you where it failed, but that's it. All right, let's see. So that's it on arrays. And there are problems on arrays. All of these problems involve loops. Naturally, arrays just ask for loops. So an array is a sequence of things. And so we don't write a separate line of code to operate on each thing in the sequence. We write some generic code and we want to repeat it, execute it for each item in the array. Normally, not always, but normally. So here's some examples of problems. Here's a maximum function. Find the largest value in A. So you have to run through A, look at all the numbers in A, and keep track of the biggest one that you found. And then return that. Return the biggest value that you find in A. Return the maximum. Use test code that uses assertions. There's another problem. Count occurrences. Now the first argument to this function is an array of integer. The second problem is an integer, len, that represents the length of the array. So len is how many values are in A. And then the third argument is an integer k. That's the number we want to count how many times occurs in A. If A has 5 sevens, then if we set k to 7, the function should return 5. There's 5 sevens in A. So once again, you need a loop for that, and I want you to use assertions with test code to prove that the code is written correctly. Well, it doesn't actually prove it, but it demonstrates to a certain degree of confidence that the code is written correctly, depending on how good your test code is. So, two-dimensional arrays, you can have functions that have one-dimensional arrays as inputs. Here's a function that has a two-dimensional array as an input. Determine if A contains only zeros. So that's a variation of that example we were just looking at, where you have to look at each value and test to see that it's equal to 0. Or in this case, you're going to test to see if it's not equal to 0. That's giving you a hint on how to finish this problem. You don't need to test to see what is equal to 0. You want to test to see what is not equal to 0. That's how you solve this one. So here's another function. Are A and B identical? Do they have exactly the same values in the same order? Unlucky. We had a problem on the functions assignment, which was to implement a function that determined if a given value was lucky or unlucky, according to some specification that we came up with. Now we want to do the same thing with arrays. Is this array A considered an unlucky array by some criterion that we come up with? It's described in here. Here's another one. Ordered arrays. Is array A are the values in A in strictly increasing order? So they go up only without leveling out. So, 1, 2, 7, 33, 100, a million, a billion. Those are values in sequence that are going up, but you can't have 1, 3, 7, 7, 11, because then we've repeated the 7. So that's not strictly increasing. It's non-decreasing, but it's not strictly increasing. It's unstrictly increasing, I guess. And so there's a lot of exercises that are 6. It's important to do a lot of these till you do them until you get the hang of it. And this is the foundation of a lot of later work that's coming. How to work with arrays using loops. And here's some example quiz questions. We can look at one of these.
A question.
Yeah.
Can we make it so that in a multi-dimensional array, how would we make it so, let's say I want it to be 1, 0, 1, 0, 1, 0. Is there a way to do that?
Using the declaration?
Yeah.
You'd have to use a loop.
You have to make that
You'd have to use a loop to do that. If you wanted the array to be, if we wanted this to be, 1, 0, 1, 0, like that, right?
Yeah.
You're going to need a loop. This won't work. This isn't going to work because you could just specify it like that. This will work. But if you want a million of these, then you're going to need to use a loop.
So you just put that array inside of a loop, and then.
Yeah, I'll show you. How do we have an array A of size 100 that's just 1, 0, 1, 0, 1, 0, like that, okay? So we won't initialize it here. And I'll use I for the index. It's not a two-dimensional array. I won't use R and C. A of I equals 0. A of I plus 1 equals 0. And A of I, we're going to do 1, 0, 1, 0, right? So A of I is 1, A of I plus 1 is 0. And then here, instead of plus plus I, we'll do I plus equal 2. So we're going to skip 2 at a time. Do 2 at a time. Then we want to see if we got it right. So we got to print this out. So let's print it out. And we're just going to do plus plus I here. So we want to print out A. We'll visually inspect. Put it all on one line. So it should have 1, 0, 1, 0 with spaces in between. Well, I'll put space dot space. How's that? Spread it out a little.
Why do we have to subtract 0?
Huh?
Why do we have to subtract 0?
Subtract 0?
Yeah.
Where do we subtract 0?
Right here.
You mean add, subtract 0?
We added 1. Oh, set equals to 0, sorry.
Yeah. All right, let's see this thing work. I'm gonna put that up here. Compile and run. There it is. It didn't work very well there, did it? Is that 100? Something's wrong. Oh, I went to 30. I didn't go to 100. I mean, yeah, you can see that it works, right? So we could do 100 here. Oh, see the same thing. Twice in one lecture. There we go. All right, so this should be 100 and 100. So that's one way to do it. It's good to come up, what you just did there is you came up with a problem. And I wonder how to do this. That's how you do it. You just come up with ideas. You generate ideas and you start testing and playing. And then it really sinks in. Then you really get it that way. If you don't play with it and be creative with it, it's hard to master it, in my opinion.
For the I plus equals 2.
I plus equals 2. What's,
Right there on the top for loop.
you want to know about this? Why?
Yeah.
Well, because we set I here, okay? So if we go to the next I, we don't want to go to the next I because we're setting I to 1, but then we're also setting the 1 right after I to 0. So we have to skip over, we're modifying 2 slots, so we have to skip over those 2 slots.
So that's why that's what it was.
Yeah. So this is a good illustration of when you would use a different kind of expression at the end of the loop for the end of loop operation. Maybe to make it symmetric, maybe you do, maybe not. Just leave it like that. All right. Anything else? Next time we'll spend more time with the arrays. So, we'll probably look at some of the, it'll be Monday. The arrays assignment is due next week, I believe.
Yeah.
Yes, okay. So then starting on Monday, we'll start looking at some of the problems that you're working. Hopefully get started on it this weekend if you can, okay?